the diode, we'll see how diode is made up. Diode is made up with P and N junction. Together we are combining them. So we'll see how the holes and electrons are recombining and making depletion layer. These things we'll deal in the electronic device and circuit. But in the analog circuit, we'll see the diode. Absolutely we'll deal with the diode, but the output of the electronic device and circuit output means we are not going to study inside of the diode. We just take the circuit of diode, how it works we'll know, and then we'll apply the diode in the circuit. Is it okay? So this is the part of circuit theory. This is the part of electronic device. From the electronic device and circuit, we choose the element, like suppose, for example, I'm saying we choose the diode out of it. Now here in the circuit I'll apply the diode. So I should be having knowledge of how diode works in the circuit. So in the analog circuit we are not going to study it deeply because we already did in the electronic device and circuit. In the analog circuit I had to mean with the diode only and diode characteristics. So I can apply the diode in the circuit and I can calculate power, current or voltage in the circuit. Okay. So let me start the subject. Before going to start, we'll cover some basic points related to this subject. Wait a minute. Friends, our subject is analog electronics. Okay. Or I can say analog circuit, sorry. For EC and instrumentation, we are getting 11 to 13 marks every year in the gate from analog circuit. Okay. And it's very easy to get 9 to 10 marks out of it because this subject is analog circuit is very interesting subject. And easy as well, right? So friends, if we talk about the analog, see how it differs from electronic device and circuit. Electronics, device and circuit. In the electronics and device and circuit, if you are talking about the diode, so diode is like combination of two semiconductors, P and N junctions. We are connecting like this, A and B. Okay. We'll study how here the holes and electrons are recombining. So they are making depletion layer over here. So we'll all study in the electronics device and circuit. From this, the output of the diode will come like diode. The symbol of the diode is like this. When we'll connect the diode in this way, it will be in forward bias. When we'll connect the same diode with this way, it will be reverse bias. Right? In the forward bias case, diode will be short circuit. In the reverse bias case, diode will be open circuit. Like this. This we'll study in analog. So in the analog, we are not going to study it very deeply how it works. We have to just mean with the working of it or characteristics of the any element. It may be transistor or it may be diode, FET, whatever it is. Is it okay? So this is about the analog. So the name is given analog circuit. So we are using this element into the circuits and calculating whatever they're asking to us. Is it okay? So let's start the subject, friends. The course outlines, we will talk about this. The first unit, I divided the entire subject in 4 units. The first unit is diode circuit. Second is BJT, FET biasing. In the next, and this one is the very important because this covers 70% part of your gate questions. For EC and instrumentation, for EE also, mainly we are getting 70% of the questions from this background, op-amp applications. We are getting questions from operational amplifier, right? And we are getting the questions from this portion and this portion mainly, right? So the first unit, if we'll talk about, is the diode circuit, and second BJT and FET biasing. Third one is the op-amp application, and the last one is negative feedback oscillator, negative feedback amplifier and oscillators, and also we'll see the power amplifiers. So today we are going to start the first unit, and In the first unit, we'll see the characteristics of the diode, clippers and clampers. These are the application of the diode. We'll see generator, rectifier, and etc. So many topics, individual subtopics are there. So we are going to study them also. Is it okay? Now, the first diode circuit, what is the learning objective? To know about the diode circuits, we'll know how the diode is working, diode characteristics we'll see in this. To discuss about the biasing of the diode, we'll see the biasing, how we can connect the diode with respect to the battery. Is it okay? Then in the next one, we'll deal with the various application of the diode. Is it okay? So let's start the diode. A pure silicon crystal or germanium crystal is known as an intrinsic semiconductor. I think you heard about this. The silicon and germanium, they are semiconductor, right? They are semiconductor devices. If we'll talk about the pure silicon or pure germanium at room temperature, it will act as an intrinsic semiconductor. Intrinsic semiconductor means the semiconductor in which the doping is zero. Okay, the outer element or foreign elements are zero inside of it. Right? No doping at all. Doping is zero. Doping means to add the impurity in the silicon or germanium atom. Doping is zero for intrinsic semiconductor. So there are not enough free electrons in the intrinsic semiconductor or SI. We don't have the free electrons, right? But for the electricity conduction, we need free electrons. So we add some impurities into the intrinsic semiconductor, or I can say the pure semiconductor. You have to add the impurities. Then you can convert this pure semiconductor in two types, P-type semiconductor and N-type semiconductors, right? Wait a minute. I'm sorry. So we can convert the intrinsic semiconductor by adding the impurity in it in two types, P-types and N-types. In the P-types, see, by adding impurity atoms to the crystal to increase either the number of free electrons or number of holes. When a crystal has been doped, it is called an extrinsic semiconductor. Okay, there are of two types. When you are adding the impurity into the pure intrinsic semiconductor, or I can say the pure semiconductor, it will become extrinsic semiconductor. And we are having two types of extrinsic semiconductor. One is N-type, second is P-type. In the N-type semiconductor, having free electrons as majority carriers. Actually, if we'll talk about the SI atom, it has 4 electrons in the outer energy cell, right? So when you will add the pentavalent impurity in it, pentavalent impurity, the 4 atom of the impurity atoms will make covalent bond with 4 these valence electrons, and 1 will remain. So this remaining or excess in electrons will constitute N-type of semiconductors, because in the N-type of semiconductors we are having electrons as a majority carriers, right? When you are adding pentavalent, see, like boron, just take the boron. If you are adding the boron into the silicon atoms, so boron has 5 electrons in its outer cell. So 4 electrons will recombine and make covalent bond with the silicon valence electrons, and 1 will remain with, right? So like that, we are having majority carriers electrons in the N-type semiconductor. Similarly, if you add the trivalent impurities to the silicon atom or germanium atom, you will get one deficiency of electron. Okay, deficiency of electron, and that because of this we call the deficiency of electron is the hole. So in the P-type semiconductor, having free holes as a majority carriers means number of absence of electrons is more in the P-type, and in the N-type we are having more and more electrons. Is it okay to you? So we are not going to deep inside. Why? Because this is not our part. Because to study this diode and all, this is the matter of electronic device in the circuit. Here we'll fetch the output. So we were talking about the diode. What is the diode? This is the terms related with the semiconductor. Now come to the diode. Based on this N and P semiconductors, now we'll be having diode in our hand now. Diode. If a junction is made by joining P-type semiconductor, let's take P-type semiconductor. Okay. I had told you about this p-type and n-type briefly, so now you're having idea about what is this. And n-type. Just combine p and n types of semiconductors like this. So they'll make a junction over here, okay? If a junction is made by joining p-type semiconductor to n-type semiconductor, a useful device is produced known as diode. If we'll add one p-type semiconductor with another n-type semiconductor, we'll be having one diode in our one device in our hand, and that device is diode. Diode represented by this symbol. Okay, this symbol represents the p-type and this is n-type. Is it okay to you? Now it will allow current to flow it only in one direction. These are the characteristics of diode we can understand like this. It will allow current to flow through its one direction only. Friends, please remember, diode conducts in one direction. This is the unidirectional element, okay, because the current will conduct in one way only. If you remember, in the electrical circuit we have seen, if you will bias it, later we'll know about the biasing, right? Biasing. If you apply the positive terminal to P side and negative terminal to N side, it will be forward bias. And in the forward bias, ideally, the diode works as a short circuit. In the short circuit, the current will pass. A very high current will pass in the circuit. But for the same diode, if you will bias it from the opposite, means the N type of the diode, you will connect with the positive terminal of the battery, and P type of the diode, you will connect with the negative terminal of the battery. In this case, diode will be reverse bias and it will act like open circuit. In this case, I will be 0. So clearly we can see here, in this direction diode will conduct and we are getting very high current, but in the opposite direction diode is open circuit and I equal to 0 in it. Is it okay? So the unidirectional properties of the diode allow current flow when forward bias and disallow current flow when reverse bias. I hope it's clear to you. So this is called the rectification process, and therefore it is also called the rectifier. Diode is called the rectifier, in which we are rectifying the, later we'll know about the application of diode, in which we'll see the rectifications, half wave, full wave and all. So this point will be clear there. Okay. So how is it possible that properly joining two semiconductors, each of which by itself will freely conduct the current in any direct refuses to allow conduction in one direction? Sorry, this is the direction, right? In one direction. In one direction, the current will flow. In the another direction, it will refuse to the conduction. Is it okay? This is all about the diode. See, these are the characteristics of diode. Later stage, we'll see the forward bias and reverse biasing of the diode. Let's talk about the symbol. This is the symbol of the diode. This terminal or P terminal is the anode, and this portion, negative terminal, is the cathode of the diode. Is it okay? The symbol of diode is shown in the figure. The terminal connected to the P layer is called the anode, and the terminal connected to the N layer is called the cathode. I hope this symbol and the diode is clear to you. This region is the P region and this region is the N region, right? Come to the next. Now we'll talk about the biasing of the diode. Okay, we are having two types of biasing, as we discussed earlier about this also. One is reverse bias and one is forward bias. Take one diode. See, this is the diode A and B, right? This is the N type, or I can say this is the N part of the diode, this is the P part of the diode. N part we call the cathode and P part we call the anode. Now I'll talk about these two things only, or I'll talk in terms of anode and cathode only. If the cathode terminal of the diode will be connected with the positive terminal of the battery, see, the positive terminal of the battery, and the anode terminal of the diode is connected with the negative terminal of the battery, the diode will be in reverse bias. The diode will be in reverse bias. In actual, what will happen, friends? Again, I'm telling you, this is the part of electronics device and circuit, so I'm not going into the deep, right? If this is P type, this is N type semiconductor, and we are adding them. They are making, or they are constituting depletion width, right? So this is part of positive ion will be this side and negative ion will be this side. Okay, so they'll form the depletion layer. This we call the depletion layer or space charge layer, space charge region, I can say. When you will apply the negative bias or reverse bias to this circuit, what will happen, you know, in the N we are having excess of electrons, in the P we are having holes in the excess, right? What they'll do, electrons will go to this side and the holes will go to this side. In this case, this depletion layer width will be increased, right? It will be increased. And technically, in electronics device and circuit, this omega is proportional to the, inversely proportional to the under root of VR, reverse bias, where VR is nothing but the reverse bias. When reverse bias will increase, the depletion width will be decrease, right? I'm sorry, this is for the forward condition. This is VF. In the reverse bias, the omega or depletion width is directly proportional to the under root of VR. When you will increase the reverse bias voltage, your W will be increased. Is it okay to you? So, if positive terminal of DC source is connected to cathode and negative terminal is connected to anode, the diode is called the reverse bias as shown in the figure. Okay. In this case, in the reverse bias, we are having only reverse leakage current. This is the very minimum current, reverse leakage current. This is in nanoampere for silicon and in microampere for germanium. This is the negligible current, I can say. So technically or ideally, if we'll talk about the diode reverse biasing, so diode will work as a, you know, open circuit. In the reverse bias, you can open diode ideally, right? If you are connecting diode in this way, or you are connecting the diode in reverse bias, the diode will act as a open circuit. Okay, in the open circuit the current will be zero, but in practically in the diode we are having leakage current. Which current? Leakage current, IL. Let's take it IL, and this is in nanoampere for silicon. So a nanoampere 10 to the power minus 9 ampere. This is nearly negligible current. Okay, so I hope the reverse biasing is clear to you people. Now if you come to the, wait a minute. So what is going on in the biasing? When the diode is reverse biased, then the depletion region width increases. Is it okay? We talk about this. And W is proportional to the under root VR. When you will increase the reverse bias, the width will be increased. Majority carriers move away from the junction and there is no flow of current due to majority carriers, but there are thermally produced electrons hole pair also. The second point is clear to you people. If you will connect, see, this is the P region, this is the N region. Here in the excess we are having electrons, here in the excess we are having holes. Now what you are going to connect, you are connecting the negative terminal of the battery to P type and positive terminal of the battery to N type. So all electrons will move to the outside of the N, means they are attracting by this positive terminal of the battery. All electrons will come to the positive terminal of the battery and sink over here. Is it okay? So majority carriers are going away. Majority carriers move away from the junction. This is the junction. Majority carrier are moving away from the junction. The negative voltage applied to the diode will tend to attract the holes and repel the electrons. Simple. At the same time, the positive voltage will attract the electrons towards the battery and repel the holes, right? This will cause current to flow in the circuit. This current is usually very small. If we'll talk about the minority carriers. Why? Because majority carriers are going away from the junctions, so they are meaningless to us in the terms of current if we'll talk about. But in the N type region, we are having holes as an minority carriers, or as a minority carrier. In the P type, we are having electrons as minority carriers. So these holes will be attracted by this portion of the battery, negative portion of the battery, and this negative or electrons minority carrier of the P region will attracted by the positive terminal of the battery, and they will constitute the current. And this current is very small, right? This is the leakage current, and these minority carriers, these minority holes and electrons pairs are generating due to temperature. Is it okay to you people? So because of the temperature effect, we are getting leakage current mainly. Now, since the current is due to the minority carriers, in the reverse bias we are talking about, and these numbers of minority carriers are fixed at a given temperature, therefore the current is almost constant, known as the reverse saturation current. If the temperature is fixed, see, the reverse saturation current given by ICO is a function of temperature, right? If temperature is constant, ICO will be constant or not? ICO will be constant for constant temperature or a particular temperature. Is it okay? So ICO, we take the constant quantity at particular temperature and known as the reverse saturation current. I hope this ICO is clear to you. Okay. Come to the forwards biasing now. When the diode is, let's take the symbol of diode. This is the diode. Now, this is the real picture of diode. This is the P type, N type, right? Now we have to connect the positive terminal of the battery to the P side of diode. We connected it like this. This is positive, this is negative. In this case, what will happen? See, we are going to connect the positive terminal of the battery to the P type and the P region, and the negative of the battery to the N region. In the P region, we are having number of holes as an excess element, right? Wait a minute, let me change the pen. In the P region, we are having holes. In the N region, we have electrons. So because of this positive, these holes will be repelled, and this hole will move into the N, and electrons, because of this battery, will move to the P region of the diode. Okay. So in this case, the depletion layer, here is the depletion layer with W, it will be narrowing. Okay. As you will increase the forward biasing, the depletion width will decrease. So the depletion width W is inversely proportional to the VB, under root of VB. When you will increase the VB, the depletion layer will decrease. I hope this is clear. This part is clear to you. So when the diode is forward biased, the majority carriers are pushed toward the junction. See, these are the majority carriers, and they are pushing toward the junction by the battery. When they collide and recombine takes place. Now they'll collide and the recombination will take place. Okay. So number of majority carriers are fixed in semiconductor. The number of majority carriers are fixed. They are not affecting by the temperature. So they are not coming in extra, right? In extra value. But in minority carrier, if initially you have 1000, this is the P region I'm talking about. If you are having 1000 holes and you are having minority carrier electrons 50, suppose, because of temperature will having, suppose, 100 number of electrons generated, hole pair generated. Similarly over here also 100 holes will be generated. So if we'll add them, it will be 1100. It will be 150. So 1100 and 1000, this is nearly equal. Here I took 11,000, but in real picture it's in crores and something. Billions of electrons and hole pairs are there inside the P region, right? So increment in the majority carriers is negligible, but increment in the minority carrier is tremendous. Okay. So here the number of majority carriers are fixed. That's why we can say the majority carrier of the device is fixed. Therefore, as each electron is eliminated at the junction, a new electron must be introduced. This comes from battery. Because of battery, we are getting the extra energy into the circuit. At the same time, one hole must be created in p layer. This found by extracting one electron from p layers. Therefore, there is a flow of carriers and thus flow of current. I hope this is clear, and this is the part of EDC. Okay, what we have to come up with at this stage with the forward bias and characteristic of the diode means when you are connecting the diode with forward biasing, it will conduct. Okay, the flow of the current will be possible in the forward case. In the negative case or in the reverse bias case, there will be zero current in the diode ideally, but in practically we have ICO. This is the leakage reverse current, right? So we'll come up with these two ideas. This is the detailed analysis and this is the part of electronics device and circuit. Now come to the diode as a circuit. When we will use the diode in the circuit, where we have to calculate the circuit parameters, it may be voltage, current, power or anything. Suppose we are given with the diode in the circuit, so how we will deal with the diode? So we should be having proper knowledge or enough knowledge about the diode. Let's start it. What is the ideal diode? Ideal diode. Let me take symbol of the diode. I hope you know very well now this is the cathode and this is the anode of the diode. Okay. So when the diode is forward bias, what is the forward bias means? Now you, I think, know very well. This is the condition of forward bias. So ideally, what will be the output of the diode? When diode is forward biased, a resistance offered is zero. A resistance offered is zero means what? Diode will act as a short circuit. If this is the point A and B and this is the diode, it will be short. Okay, resistance is zero. For the short circuit, resistance is zero or not. So in the forward condition, ideal diode acts like a short circuit. When it is reverse bias, resistance offered is infinite. It acts as a perfect switch. See, if you bias it in reverse biasing, the diode will act as an open circuit. Open circuit means R equal to infinity. Right? So this point is also clear to you. Now come to the picture. See. So please observe this graph. Let me take pen over here. So please observe this graph. See, this is the forward bias of the diode. When you applied the forward voltage in this region, this is the forward positive voltage, right? So in the positive voltage, as you applied, the current is infinite, means a very high current is there. V equal to Ri, right? V equal to Ri. So can I say I is nothing but V by R? In the forward region, we have seen R offered by the circuit is 0. V by 0 is infinity. So current is infinity. As you apply the forward voltage, the current will be infinity. So this graph is a representation of the forward biasing of the ideal diode. But what about the reverse biasing? See, in the reverse biasing, you applied the negative voltage. Here is the negative voltage. Here is the positive voltage. In this positive voltage case, the current is infinite. But what about this? In this region, see, V equal to Ri again, the resistance offered in the reverse bias, or when V less than 0 is infinity. R is infinity. In this case, I equal to V by R. V by infinity is nothing but 0. I is 0. See, this blue line shows the current in reverse biasing is 0. Current ID is 0. Is it okay? So this is the characteristics of diode, ideal diode I'm talking about, and forward bias and reverse bias condition. Now come to the next. The next is the practical diode. And in our questions, we will consider the practical diode only. We'll see the practical diode. Let me take pen. So what is the practical diode? When forward voltage is more than 0.7 volt, I think this also you learn in electronic device and circuit. Means, friends, if you have diode in your hand, you applied some voltage to it. This is anode, this is cathode. You applied some voltage to it, and this is forward bias of condition you can see over here. So 0.7 is the diode cut-in voltage. Means before 0.7 diode will not work. After 0.7 only it will start to work. Means this is the barrier potential. Barrier means depletion region in the PN. This is the barrier, and because of this barrier we are getting potential. See, because in the barrier we are having electric field, positive, positive, positive. Electric field will work like this. So this will oppose the applied voltage. So this is kind of barrier potential. So 0.7 is the cut-in voltage. What is the meaning of this cut-in voltage? Actually, friends, the 0.7 cut-in voltage means if you are considering the diode, you are applying the voltage. You are applying from 0, 0.1, 0.2, 8.1, diode will not work, 0.2, it will not work, up to 0.7, it will not work, and at exact 0.7, it will start to work. And I told you, in the forward direction, the resistance will be minimum, it will act like short circuit, but that is the characteristic of the ideal diode. But in the practical diode, two things we are getting. First, we are getting the cut-in voltage, or I can say this is the threshold point. If you want to start the diode, first apply it or cross the cut-in voltage, then use the diode. So what after cut-in voltage? What is the scenario after cut-in voltage? After cut-in voltage, it will offer some resistance also. After cut-in voltage, diode will become simple resistor, right? Simple resistor. What is the resistor mean? Resistor has to offer, or any element will offer the resistance. Diode will also, right? So RF of the diode will be V by E. V is the applied voltage across it, and I is the current in the circuit, or current across diode, or in the diode. Okay. So in this diagram, you can see this is the practical diode given over here. I'll show you. This is the diode symbol. The cut-in voltage is connected in series with this. Cut-in voltage, it will oppose the input, means you have to subtract 0.7, and this is the resistance of the diode over here. If you see this graph, before 0.7 diode is not working. This is the dead zone. After 0.7 it's working, but the characteristic is not like vertical line. No, not like this. Why? Because this is the case in the ideal diode, but here in actual practice we are getting some resistance offered by the diode. So this is the resistance, and resistance offered by diode is applied voltage divided by current. Is it okay? So if you write the equation, VD is nothing but 0.7 VD here. What is VD over here? VD is nothing but 0.7 plus RF into ID. Is there any problem you have? So when forward voltage is more than 0.7 volt, then the diode conducts and the voltage drop across the diode becomes 0.7 volt. This is the cut-in voltage or barrier potential. This one will be dropped across the diode. Okay, for the practical diode I'm talking about. And it will offer the resistance. Okay. So I hope the practical diode is also clear to you. Now come to the next, and that is one example I consider over here. Calculate the voltage output of the circuit shown in the figure for the following inputs. We have three conditions given over here. V1 and the first condition. Firstly, we have to calculate the output. Where is the output? Here is the output. I'll consider first condition. Okay. V1 and V2 both are 0. V1 and V2 both are 0. If you applied 0, means you are applied nothing to this. What will be the stage of diode? Nothing will be here, right? So if you applied the input as 0, the output will be 0. No output you will get, right? 0 means there is no output. Okay? No output condition. No output condition means initially output was 0. So while applying V1 and V2 as 0, the output will be 0 as it is. Okay, come to the second condition, and in the second condition, V1 equal to V volt. Where is the V? Here is the V, and V is V volt. Okay, let's take this V like 5 volt. Let's take it 5 volt. Come to the V2. V2 is 0 volt. Okay, 0 volt means this one is grounded. Now who will conduct? This will conduct definitely, because this will be in forward bias now. What about this circuit? Circuit 2, it will not conduct. Why? Again the input is 0. So no output over here. The condition is dead condition. Right? So this one will only conduct. Now your circuit will like RS. Fine. Your diode, and here is the output. Okay. And this is R. This is 5 volt you applied. Okay. Now what about the diode? If diode is ideal, you can replace this by short circuit. Simply short circuit. Okay. Because ideal diode in the forward bias condition acts like short circuit. Now they're asking for the V node. In this case, 5 volt you can divide to this R, simple voltage division rule, and you can find out the V node. Voltage division rule we have seen in the circuit theory, if you remember. The resistance across which we have to find the voltage. So V naught is nothing but across this R. So value of this R into source voltage. Source voltage is 5 volt. Over here given V volt, I am taking V divide by summation of this 2. RS plus R. So this is your answer in this case. Okay. But what if you are getting practical diode over here? Let me take the condition for practical diode. For this circuit, it will be given in the question that it is practical or ideal diode. Okay. So I'll replace diode by equivalent circuit, and equivalent circuit of the practical diode is one battery connected in series with resistance. So your circuit will become RS. This is the diode resistance RF. The potential offered by diode is 0.7. Over here V0, and this resistance is R. What about this circuit? This circuit is dead circuit. Your condition is like this. In this case, how you will find out the V0? Just apply KCL or node analysis over the V. This V0 is the same. So I'll apply over here V0 minus. I'll take this 2 branch. They are connected with 2 branch. So we are having 2 terms in one equation. Okay. Nodal analysis. V0 minus V divided by RS, and 0.7 also. This will be plus. Why? Because minus minus plus. RS plus RF. This branch is over, plus V0 divided by R. Is it okay? Equal to 0. So you can find out by calculating this equation, you can find out the value of V0. So this is the way to solve. Okay. Now come to the third portion of the question, and in the third portion they are saying if V1 V2 equal to both are V, new voltage VR. Okay. So the forward resistance diode is RF. Means this condition is given as we have to consider the practical diode over here. Is it okay? So in the third case, both inputs are same. Let's take 5 volt over here. Both diode will conduct. I can replace the diode with RF and 0.7 like this. This is RF and this is RS. RF is given already. But see, in this case, they are not given with the potential 0.7 drop. Okay. So whenever they will ask the question, they will mention it. If they don't mention it, we have to take it short circuit. Means we have to take it 0 volt. Is it okay? Here I am showing by taking 0.7 because this is the practical diode I going to consider for this. Here the voltage is take 5 volt. This will work. No problem at all. Here V0, and V0 is across R. Okay. Here the situation is same. You are having RF in series with RS and again 0.7 battery, and this is 5 volt. Now your task is to calculate V0. So to calculate the V0, again you will apply the node analysis as V0. So V0 minus plus 0.7 minus this 5, or you can take it V because they are given with V. This is V RS plus RF. This same equation will come 2 times because these 2 branches are very same. So you will multiply with 2 plus V0 by R equal to 0. Again, you can solve this equation and you can get V0 value. I hope this is clear to you. Is it okay? Now let me take some examples from GATE exam. Okay. One question is given and the question is, let me draw it. This is plus 5 volt connected with 2.5k resistance. Over here we have diode and this is grounded. Here we are taking output plus V, or let's take it V0, and current in the circuit is I. Okay, and this is 2.5 and 5. Now the question is, assuming the diodes to be ideal, find the value of I and V. This diode is ideal, condition is given. Your diode is ideal. Okay, and you have to calculate V0 and I. Is it okay? So if you'll see this circuit in the first side, you can say this diode will be forward biased. Why? Because at the negative terminal of the diode, it's connected directly to the ground. So obviously the potential at the P terminal will be higher than the N terminal. Why? Because the positive of the battery you applied to the P type. Okay, some drop will be there across 2.5k. But at the end here the potential will be higher than this, right? Because the N part of the diode is directly connected to the ground. So this will be forward bias. Okay. So once you identify the circuit or the diode is forward bias, you can replace the forward bias diode by, if you remember, by short circuit. Is it okay? The diode in forward acts like short circuit. Here is the V0. Here is the current in the circuit and this is 5 volt you applied. Now see, he's asking for V0 and I. Can you find V0 for me now? Yeah, V0 is directly given to the 0. Why? Once the diode is short, the voltage is become 0 volt. Is it okay? Because this V is directly connected to the ground now without any resistance in between. So V0 is 0. What about I? Simply there is the potential difference. This I is nothing but 5 minus 0. 5 minus 0 divided by 2.5k. Is this k? Yes, this is given as the k, right? So this is 2 milliampere. So answer is V0 is 0 and I is 2 milliampere. Is it okay to you? Now come to the next question. This was a bit easy. Now I'll take a bit tedious one. Let me clear it first. In this question, the circuit is like you have D1. In this way, you have D1. Here you have D2. Like this. They are connected. And here I have 5 kilo ohm resistor and minus 10 volt. Okay. Across this D2 I'm taking output V0 and here it's connected the resistor 10k, the battery plus 10 volt over here 10k, they are connected to each other, and here I'm taking V0. Okay, like here V0 is the output. I'm taking output across D2. And the current in D1 is given like this. Okay. Now the question is, both diodes are ideal, and the question is find out V0 and I0. Or I0, not it's I only. Is it okay? Now friends, directly you can't say that D1 and D2 they are working in forward bias or reverse bias. So how to solve this type of circuits? How to solve this circuit? See, can you say me this? What is the diode D2 condition, whether it's forward bias or in reverse bias? How? Because you don't know what is the potential at point A and what is the potential at point B. Do you have? No. If you are having this resistance as 0, so potential or the terminal B is connected to minus 10 volt. In that case, I can say the D2 will be in forward bias, because definitely this potential will be at positive terminal, positive potential, because this 10 volt battery is connected to A. Is it okay? What about D1? We don't know the potential over the point C. This potential C, the P type or P region of the diode is connected with the 0 volt. Okay, fine. But if this voltage is in negative, in that case, the D1 will be in forward bias. But if the point C is positive, it will be in reverse bias. But I don't know what is the potential at C. So how to solve this type of circuit? I'm telling you the procedure for that. Okay, let me erase it first. Whenever, if you encountered with this type of condition, what you have to do is, the first step is make diode short. Means you have to do, what you have to do is, you have to take short circuit of the diode. Means you have to assume they are connected in the forward bias. Okay, later it will be clear out if our assumption is wrong. So don't worry about this. The very first step is make the diode short circuit, or consider the diode in the forward bias. Consider it by default. If you will consider this diode in short circuit, so I can remove this diode and it will be act like this. Is it okay? What about the D1? It will like short circuit. Both D1 and D2 now short circuited. Is it okay? D1 and D2 both are short circuited now. Let me clear it. Okay. Once they are short circuited, now this is the simple circuit problem. You can solve it. Let me change the pen color. Okay, fine. Once the D1 is short circuited, this 0 is directly over here. This is 0 volt. Fine. If this is 0 volt, this is also 0 volt, because they are connected with one wire. Simple short circuit. Okay, there is no any resistance in between this. So V0 is 0 simply. In this case, V0 is 0. But we have to check our assumption is correct or not. Is it okay? See, how to find this, that our assumption is correct or not? Can I apply over this point C node analysis? Yes, I can apply. If I'll apply the node analysis at VC, and VC is 0, because this is directly connected to the ground. So 0 minus, and this minus will become 10 divided by 5K. Is it okay? The current coming from this is I, and this is the incoming current. I have to take with negative sign, if you remember. What about this? This is 0 minus 10 divided by 10K. Is there any problem with this equation? This is the simple nodal analysis. Okay. So I can take this I to this side. It will be 2 milli minus 1 milliampere equal to I. So when you will calculate I, it will be 1 milliampere. See, the sign of the I, or the polarity of the I, or the direction of the I, this is the positive. Positive means whatever direction is given in the circuit is absolutely right. See, for this current I, current is coming from this side. We assume this incoming current while solving the equation here. Means our current is correct. If we are getting the current value in negative 1 milliampere, it means the direction is wrong. The direction is opposite in actuality. So here the current value is positive, means whatever the direction of current you took in the equation is perfectly right. Okay, means current is coming from ground to this point. Here initially we had D1. Is it okay? Now tell me one thing. If you have some diode like this, and in the diode if current is flowing in this way, the diode will be forward bias or reverse bias? Tell me. It will be definitely forward bias. In the forward bias, the current will pass in the diode from P to N. Yes, in this case P to N I am having current. The diode is working. The diode is working means it is in forward bias. So whatever I assumed in the first step, make the diode is short. For the diode D1, the condition is very clear that yes, I was right. To assume the diode D1 as forward bias, I was completely right. This part is over. Now come to the D2. Here I had D2 connected, right? So can I find out the current in this? Yes, I can find out. See, this is the 0. Potential difference is given. So I assume this ID2. ID2, if I'll talk about ID2 will be 10 minus 0 divided by 10K. It will be 1 milliampere again. What is the direction of the ID2? The direction is from up to down. Up to down, here the ID2 will encounter with D2. The condition of D2 is given like this. In the D2, current is coming from P to N. It means this one is also in forward bias. Is it okay? So means whatever output you get is completely correct. V0 is 0, and second one they ask for the I you already calculated. This is 1 milliampere. So this is about this circuit. How to solve it, I think you know now. Whenever you go this type of situation, first make the diode shorts, then find out the various parameters of the circuit, and then please check whether your assumption is correct or not. Let me take another example. Okay, come to the next one. The next question is given as, this is 5K. Here diode D2 like this. This problem is same as the previous one, but have some changes. This is D1. Okay. 10K and minus 10 volt. Okay. This is V0 over here, 5K, and this is 10 volt minus, everything is same, but situation is changed. Situation is like here the resistance is now 5K. V0 is same. The current in the circuit is same. Let me take it. Let me change the color first. Here the current is given I over here. The condition is the both diodes D1 and D2 are ideal. Find out V0 and I. This is your question. Now what is the step? I told you last time. Assume diodes D1 and D2 in forward condition or in short circuit. Okay. Make them short. If you will make the short and you will analyze the circuit will be, let me remove it because I had to short D1. Okay. And let me remove D2 also. I'm going to short them. I'm going to short D2. I'm going to short D1. Okay. When you short it, this 0 is directly coming to here and directly coming to the V0. In this case, V0 is 0 volt. Okay. If V0 is 0 volt, now can I come with this current I? Yes, I can come with this current I. The current I is, or see, I have to check the conditions of diode, whether my assumption is correct or not. So I have to find this current and this current because the diodes are connected in these two branches. I need current direction so I can judge that my assumption is right or not. See, if you'll apply the nodal analysis at this point is, let's take, this is 0 volt point, right? So I can find this I and this both. So I can find out the condition of diode D1 and D2. Let's apply nodal analysis over here. So this is 0 volt minus minus minus, it will become plus 10 divided by 10k. The current is incoming current over here, so I assumed I. And in this branch, third branch, the current is 0, minus 10 divided by 5k equal to 0. Is it okay? This is the single equation in which I have single variable, and that is I. So this 10k, this is 1 milli, this is minus 2 milli equal to I, if I am right. So I is minus 1 milli. Now, in the last question we were getting this positive, but here it's negative. Negative means whatever direction you assumed is completely wrong. The current in this diode will be from this side. Is it okay? So initially the diode was connected over here like, let me take the diode. The diode was connected over here like this. If current will flow in this way, the diode will be definitely in off state or reverse bias state. It means my assumption is wrong. Whatever I assume is completely wrong. Further, I have to study and make some changes. So I know the condition of D1. D1 is in reverse bias. What about D2? What about this current? Definitely this current will come from 10 to 0. This is at lower potential. This is at higher potential. And ID2, if you will find out, it will be 10 minus 0 divided by 5k. This current is nothing but D2 current, 2 milliampere. The current direction and diode direction is same. So diode D2 is in forward bias, diode D1 is reverse bias. So I have to replace with this original one, okay? Because whatever I assumed earlier is wrong. I have to change it now, okay? So let me change it. Okay, fine. Let me erase it all. I have to make some changes in the circuit. And those changes are, I have to replace D1 as an open circuit because the D1 is in reverse bias. So this is D1 over here. I'll replace it as an open circuit. This 0 will remove from the circuit and it will be forward bias. I'll short it, make it short. Okay. Now this is no longer 0 volt. Now your new circuit will be, if you'll draw it, your D1 is open circuit. Okay. Fine. Your D2 is short circuit. This is D2 over here. Now this is your circuit. Now you can solve this circuit very easily. Here don't know voltage, only one current in the circuit. You can start from 10 and you can end your journey to minus 10 to get current I1. Is it okay? Or you can apply some nodal analysis by assuming there's some voltage. I have to find we have to find V0 and I0. So let's take it. V0 is the voltage over here. Is it okay? So directly we'll find it by nodal analysis. Nodal analysis say V0 minus 10 divided by 10k plus V0. This is minus 10 divided by 5k equal to 0. Is it okay? One equation, two terms, because two branches are connected. This branch is open. So this is meaningless over here. So friends, take LCM. This will be 10k. Okay. V0 plus 10 plus 2V0 minus 20 equal to 0. Am I correct? Yes. 10 to 10. This 10k will go this side and 3V0 equal to 10. V0 equal to 10 by 3 volt. Is it okay? Now V0 is 10 by 3 volt. What is the value of I? Here the voltage is 10 by 3. Can you find the value of I? I is nothing but potential difference 10 minus 10 by 3 divided by 5k. Is it okay? So this will be 30 minus 10, 23 by 5k. So this is current is 4 by 3 milliampere. Is it okay to you? So this is the current in D2. But in the question he asked for the D1 current. This was the current in D1, right? So the D1 current is absolutely 0 because this is the open circuit. So your answer is V0 is 3.33 volt and I is 0 volt. I hope this is clear. We'll meet in the next class with some more problems and application of the diodes. Till then, take care and bye.